In the standard TDA pipeline, which means topological data analysis, the workflow is linear. We move from raw data to a geometric structure and finally to a barcode, a persistence diagram summarizing the holes across scales. However, a significant bottleneck arises when we attempt to move right to left. If a specific bar in a barcode represents a critical structural pattern, how do we identify the specific data points responsible for it? Traditional homology identifies these features as equivalence classes. Any two cycles are identical if they differ only by a boundary, a filled-in higher dimensional shape. Consequently, there are mathematically infinite ways to draw a loop around a hole. Standard software provides a non-unique, messy cycle via matrix reduction. Without a canonical choice, we cannot reliably map topological features back to specific data points for biomarker discovery. The pipeline begins by transforming discrete data points into a continuous geometric shape called a simplicial complex. We denote the set of p-dimensional samplices, vertices, edges, triangles, as k sub r raised to p. Via torus rips/alpha complexes connects points into p-samplices based on a proximity parameter r, resulting in a static geometric representation at a fixed scale. A monotonically non-decreasing function that builds nested subcomplexes, filters the sequence of growing complexes k sub r and reveals what we call feature persistence. We define the boundary map, del p, to distinguish between different types of shapes, cycles, kerneled chains with no boundary, del z equals 0, and boundaries, image cycles that are the boundary of the p+1, simplex. Standard homology, HP, is the quotient of the kernel over the image. This creates a choice problem when seeking a representative cycle. The harmonic shift occurs when we use real coefficients and inner products. In applied TDA, we typically use C sub 2 coefficients. However, the harmonic approach utilizes real coefficients, R. While this may seem different for discrete topology, it is technically necessary to turn the chain group into a Euclidean space. We define the harmonic homology subspace as the intersection of the space of cycles and the space orthogonal to the boundaries. Defining the inner product, we declare the basis of all p-dimensional samplices to be an orthonormal basis. The scalar product sigma I, sigma j is 1 if I equals j and 0 otherwise. This inner product allows us to define the orthogonal complement of a subspace. This shift allows us to project any messy representative cycle into a unique, optimal form residing in H sub p. Within any homology class, some samplices are essential. An essential simplex is one that must be included in any cycle that loops around that specific hole. If removed, the cycle cannot close. The harmonic representative is the unique cycle that minimizes the Euclidean L2 norm while maximizing the relative essential content. Because ZH minimizes the L2 norm, the denominator, while maintaining the coefficients of essential samplices, which are already orthogonal to the boundary, it naturally highlights the most critical non-negotiable edges of the topological feature. Computationally, the harmonic representative acts as a harmonic flow. Much like current in a circuit, the weights diffuse across the complex. In this flow, the circuit around the hole is non-zero, but the divergence at each node is 0. The harmonic pipeline for diffusion and calculation is as follows. Extract representative. Obtain an initial cycle from standard boundary matrix reduction. Compute orthonormal basis. Use the boundary matrix at the time of the bar's birth to find a basis for the space of boundaries. Project to orthogonal complement. Remove the boundary component of the cycle to find the L sub 2 minimal version. Disentangle multi-way interactions. If multiple bars, holes, overlap in the barcode, ensure the representative is orthogonal to all other living harmonic representatives to guarantee uniqueness. In computational biology, these weights transition from abstract topology to harmonic features. By aggregating weights from the edges onto the nodes, e.g. genes or patients, we create a new feature matrix for machine learning. The biological sample patterning can help identify the specific cluster of genes forming the loop in a correlation-based complex in gene expression. Assist methylation data simulations by allowing complex diffusion of weights to help identify which methylation sites are essential to the structural stability of a disease subtype. Aggregating complex harmonic features allow for clustering patients, e.g. luminal A versus basal, based on their topological importance, specifically for cancer subtyping. The Harmonic TDA pipeline fundamentally bridges the gap between abstract topological features and concrete, actionable insights in biology. Harmonic TDA replaces ambiguous equivalence classes with a unique canonical representative for every bar in a barcode. By adopting real coefficients and L2 norm minimization, we find the minimal energy representative that maximizes essential information. Actionable harmonic features. The weights generated by the harmonic flow act as a bridge, allowing researchers to trace abstract wholes back to the specific genes or samples that define them. Download this interactive tutorial, along with an in-depth explainer on the Patreon linked in the description. This Harmonic TDA tutorial is paired with a feature persistence explainer, which goes more into introducing dimensionality to simple barcodes, revealing nested complex features.